Welcome, humans, and any celestial body else out there listening. This is Curious Minds, Infinite Answers. I'm your host, Courtney Christine Koskin. This podcast, simply put, is a mix of human curiosity and how, with the help of AI technology, curious minds can get the answers we seek. Let's get mind-bending and plunge deep beneath the surface of our everyday thoughts. Let's begin. Imagine this. You're outside on a calm, clear night, looking up at the stars. It's peaceful. The vastness of space stretching out above you. Suddenly, a shooting star streaks across the sky. You smile. Maybe make a wish. But what if that streak of light wasn't just a rock burning up in the atmosphere? What if that light had come from another dimension? Today, we're going to explore that question and so much more. We're diving into black holes, wormholes, and the concept of the singularity. But first, we need to go back to the person who set the stage for all of this, Albert Einstein. Everyone knows Einstein, the wild-haired genius who gave us the theory of relativity. If Sir Isaac Newton is the father of physics, then Einstein's like the rock star of physics. His work reshaped how we understand space and time, showing us that space and time are connected and that gravity isn't just a force pulling things together, but the result of mass warping space-time. Imagine space like a big, stretchy blanket. When you put something heavy like a ball on that blanket, it makes a dip. Big things like the Earth or the Sun make dips in space. When smaller things like the Moon roll close to the Earth's dip, they follow the curve and stay close. That's what we feel as gravity. So instead of being pulled, things are sliding along the curves of space. Cool, huh? Okay, curving on, relatively speaking. Late in Einstein's life, he was chasing an even bigger idea, a dream he called the unified field theory. His goal was to find one theory that explained everything: gravity, electromagnetism, and all the forces of nature. Unfortunately, he never quite finished. The tools of his time weren't advanced enough, and the mysteries of the universe remained just out of reach. However, his work led to some of the most mind-blowing concepts we know today, including the idea of black holes. These are some of the strangest objects in the universe, where the very fabric of space and time become twisted in ways we still don't fully understand. So what exactly is a black hole again? You've heard of them. These mysterious, invisible objects in space that seem to suck everything into them. In 2019, we even caught a blurry glimpse of one thanks to the Event Horizon Telescope collaboration. If you're curious, you can search it online and check out the image. Okay, so let's break it down a little bit further. A black hole is essentially the remains of a massive star that has collapsed under its own gravity. As the star collapses, its gravitational pull becomes so strong that not even light can escape. There's a boundary around the black hole called the event horizon, just like the telescope, yes. The event horizon is the point of no return. Imagine you're standing at the edge of a waterfall. Once you cross that edge and go over, there's no swimming back up the falls. Currently, we believe anything that passes is trapped forever inside the black hole. But the real mystery lies at the center of the black hole in a place called the singularity. A singularity is a point where all the mass of the black hole is compressed into an infinitely small space, and the laws of physics, as we know them, break down completely. It's a place of infinite density, where space-time becomes infinitely curved. In simpler, yet not clearer terms, it's where things get fairly weird, as far as we can comprehend within our scope of understanding. Did you see the movie Interstellar? Remember when they're traveling through the black hole and they start appearing super stretchy and spaghetti-like? Well, outside of cinema and back in reality, we wouldn't actually send humans through a black hole because black holes have insanely strong gravity, especially near the event horizon, the point of no return. As you get closer to a black hole, the gravitational pull becomes so strong that it stretches anything that falls into it. But just for curiosity's sake, say, here we are sending someone through. You can expect that they're being stretched and elongated like a piece of spaghetti. What now? Stretched? How have they not just been pulled apart in two? The reason a person falling into a black hole would be stretched rather than simply pulled apart right away comes down to the way gravity works across different parts of their body. This process of stretching is called spaghettification. Basically, you'd be stretched first because of the increasing difference in gravitational force between your feet and head as you fall deeper into the black hole. This is what makes the process gradual, rather than an instant tearing apart. Man, talk about some out-of-this-world torture. Well, if that wasn't gruesome enough, let's talk about the crushing force at the singularity. After being stretched, the person would be pulled toward the singularity, the center of the black hole, where gravity is infinitely strong. At this point, everything, including the person, would be crushed into an infinitely small point. So, long story long, black holes have such extreme gravitational forces that falling into one would be a painful and fatal process, which is why sending a human through one is definitely not a good idea. As we venture down the rabbit hole, learning of curves, points of no return, extreme gravitational pressure, and infinitely small points. Wait. What is singularity and how does it tie in with the black hole we've just learned about? I ask because sometimes I need to read or hear things a few times to get it to stick. And I'm not a scientist, and I have a very feeble but open and ever-evolving mind. Okay, real quick recap. A black hole forms when a massive star collapses under its own gravity after it runs out of fuel. As it collapses, its core becomes denser and denser until it forms the singularity, the core point where all the star's mass is concentrated. At the singularity, the density is thought to be infinite, meaning that the gravitational pull there is also infinite. This is what causes the intense gravitational forces that pull everything, even light, into the black hole. This really is quite fascinating and frustrating, because at the singularity, the forces of gravity become so extreme that our current understanding of physics, including general relativity and quantum mechanics, breaks down. This means we don't fully understand what happens inside the singularity or how to describe it mathematically. It's a place where the known laws of the universe stop working, and that's why it remains one of the biggest mysteries in physics. Let's continue to travel through space and time and briefly connect the next topic. Wormholes. Thank you again for being here, and thanks to Einstein and Newton for inspiring this talk. Wormholes. They're like tunnels through space-time. They are a theoretical concept. Scientists haven't actually found one yet, but the math suggests that they could exist. Think of a wormhole like a shortcut between two distant parts of the universe, or even a passageway between different dimensions. Cool. This is where light comes in. Light is special because it doesn't have mass, and it travels at the speed limit of the universe. I didn't even know the universe had a speed limit. Who's enforcing that? Slow down, star! All right, let's break down why light is so special. Well, for me, it's because I was afraid of the dark well into my teenage years, and my little sea turtle nightlight gave me hope and comfort as I slept through the night. I digress. Here's why it's more special on a massive and universal level. No mass. As previously stated, unlike most things in the universe, like people, planets, or even tiny particles like electrons, light has no mass. That means it doesn't weigh anything. Most objects with mass need energy to move, and the more massive something is, the harder it is to move quickly. But since light has no mass, it isn't held back by the same rules that apply to things with mass. In Einstein's theory of relativity, there's a universal speed limit. Nothing can travel faster than the speed of light, which is about 186,000 miles per second or 300,000 kilometers per second. Since light has no mass, it's able to travel at this maximum speed naturally. Ultimately, light moves as fast as anything possibly can in the universe. In conclusion, light is special because it's massless, so it can always move at the fastest possible speed in the universe, what we call the speed of light. Nothing with mass can ever go as fast as light because mass slows things down. Peace be with you. Could light be the key to traveling through wormholes? What if, instead of being trapped inside a black hole, light could escape through a wormhole and end up in another part of the universe, or even in another dimension? Now, let's go back to that shooting star. You see a streak of light across the sky, and you think, it's just space debris burning up in the atmosphere. But what if that light is actually slipping through a wormhole from another universe? It's a wild idea, but it opens up some amazing possibilities. Could light be moving through different dimensions, showing up in our universe as what we think are shooting stars or unexplained bursts of energy? Let's dive deeper into what's called the holographic principle. This idea suggests that everything happening inside a black hole could be encoded on its surface, the event horizon, that place of no return. Imagine a 3D object being stored as a 2D image on a screen. The information about the 3D object is still there, but it's been flattened into a different form. This theory could help solve the black hole information paradox. The black hole information paradox is a puzzle in physics that arises from the conflict between general relativity and quantum mechanics. It suggests that when something falls into a black hole, the information about it is lost forever, as it is absorbed by the singularity. However, quantum mechanics states that information can never be destroyed. As you can see, this paradox challenges our understanding of how the universe preserves information and remains an unresolved issue in modern physics. But not all hope is lost. The holographic principle offers a solution. What if the information isn't lost, but simply stored in a way we don't fully understand yet? Thank you, Gerard Hooft, a Dutch theoretical physicist, for proposing the holographic principle in the early 1900s. Let's bring us back to light. Could light be encoded on the surface of a black hole, preserved in some way? Or could it be transferred through a wormhole to another part of the universe? If the holographic principle is correct, then maybe black holes aren't just cosmic dead ends. Maybe they're gateways to other realms of space and time, and light could be the key to unlocking them. All right, here's where things get even more exciting. We know light doesn't have mass, and it moves at the fastest speed possible. In the world of quantum mechanics, light can do some strange things, like quantum tunneling, where it passes through barriers it shouldn't be able to cross. So, what if light is the one thing that can actually travel through black holes or wormholes and come out on the other side? Side note to Dr. Neil deGrasse Tyson and your peers, please do not come after me. This is all hypothetical. Thank you. We've seen strange bursts of light in space, gamma ray bursts, and fast radio bursts that we don't fully understand. Could these be signals that light is traveling through wormholes or from other dimensions? Maybe we're seeing glimpses of light from a part of the universe that's normally hidden from us, slipping through cracks in space-time and appearing in our sky. It's speculative, sure, but that's what makes it so intriguing. The more we study light, the more we realize how little we know about its full potential. Light might just be the key to understanding the hidden structure of the universe, and maybe even the existence of other dimensions. And now we come full circle, back to Einstein. His final endeavor was to create a unified theory that explained everything, from gravity to electromagnetism to the behavior of light. He never quite finished it, but his work opened the door to all of the questions we've been asking today. Einstein's theories laid the foundation for how we think about black holes, wormholes, and the nature of the universe itself. And today, scientists are using advanced tools like the Event Horizon Telescope and gravitational wave detectors to explore these mysteries. With each new discovery, we get a little closer to answering the big questions. Maybe one day we'll figure out if light really can travel through black holes or wormholes. Maybe we'll learn if black holes are truly cosmic dead ends, or if they're actually gateways to other dimensions or parts of the universe. We don't have all the answers yet, but that's the beauty of exploration. The more we ask questions and stay curious, the more we learn and uncover. Can you imagine if humans weren't a creative and curious species? I mean, think about how far we've come for a second. Humans would have never thought of traveling beyond their caves or villages. And then we went from hoofing it to putting other hoofs to work by riding horseback. From there, we couldn't have imagined a powered engine that would cut travel time in half, as well as enable us to cross the open seas and the broader countryside. But then came steam engines and railroads. Moving along, we evolved again, thanks to the tenacity of a young man from Michigan who pioneered the automobile industry and made it affordable to the middle class. Fast forwarding through time, we're in the skies, flying from one part of Earth to another. So look, if we can accomplish all of that, and here we are now living in the fastest technological era to date, who's to say we won't one day find the tools to be able to encode light, send it through a black hole, and find out what's on the other side. Hey, thanks for going through all these realms of possibility with me. I love asking questions and finding all the possible answers, but even more so, imagining the what ifs. The possibilities are endless. Just remember, it's all relative, in theory. And on that note, I'd like to leave you with my favorite quote from Albert Einstein. Short, sweet, and absolutely true. Imagination is the preview to life's coming events. Thank you for tuning in to Curious Minds, Infinite Answers. I'm Courtney Christine Koskin, and I hope you'll join me for next week's episode as we proceed down the path of curiosity and discovery, uncovering various topics along the way. If you have any comments or want answers to your burning curiosities, drop me a line in the comments below. Until we meet again, find the good in the world, and if you can't find it, be the good.